Hello, everyone. My name is Shashi Khanal. I'm a master's student in the computer science department. My thesis supervisor is Dr. Rajiv Iqbal. Our research title is Video Error Concealment Using Neural Network. As you know, loss of video data transmitted over the internet is unavoidable during transmission, so we need to fix the loss of data. One widely used approach is video error concealment. There are popular error concealment techniques like motion vector prediction, which is used in HEVC. HEVC is the most advanced and latest video codec to date and is used by almost all multimedia applications worldwide. Today, the power of neural network is harnessed by many applications, but the video error concealment technique, motion vector estimation, which is used in the most advanced video codec, HEVC, does not do it. So in our research, we are exploring neural network for video error concealment. In particular, we use convolutional neural network, which is known as CNN, to predict the voxel information of the lost part of the video data. Our model could replace or be used interchangeably with the existing error concealment technique in the HEVC codec. Our main motivation behind this research is to take advantage of neural networks in video error concealment. This way, we improve the quality of error concealed video. We also compared the performance of our proposed model with motion vector estimation and error concealment using neighboring motion vectors technique. There are promising methods based on deep neural networks presented by different authors where GANs and impending models are used, like Finnegan and generative image impending models give good results. However, these techniques are not proved to work for video error concealment. Our error concealment neural network model is based on a deep convolutional neural network. It consists of two data flows as shown in figure 1, which when separated can exist as two independent CNN models. The outputs from each of these two paths are used to get the final error concealed video frame. It can be treated as a simple non-sequentially stacked neural network model comprising of CNNs, which flows through two paths and converges at a point. Errored video frames along with passed frames are passed to the top path of our network, and voxel information of error concealed video frame is predicted. Similarly, errored video frames along with future frames are passed into the bottom path of our network, and voxel information of error concealed video frame is predicted. Both the predicted voxel information from top and bottom paths are combined to correctly predict the lost part of the video frame. In our proposed approach, both the top and bottom paths are independently trained like any other CNN model. We use Celeva and Hollywood 2 datasets. After the training, both layers are saved as different deep neural network models. Then at the time of error concealment, when frames are being received, both the said models are loaded and connected by transfer learning, as shown in figure 2. This newly formed network for transfer learning is trained again on the fly with available video frames as training data. Transfer learning is utilized because it repurposes the already trained model. The upper path model is trained with 200 past frames or less if fewer past frames are available. And similarly, the lower path model is trained with 200 future frames or less if fewer future frames are available that come after the errored frame. 200 past and future frames were used so that our model takes less training time and gets enough training data to reasonably produce the output. Altogether, our newly trained network predicts two corresponding outputs, and we combine collocating blocks of data from these outputs that are lost in the errored frame. Finally, we put these combined blocks into the errored frame, which ultimately gives us the error concealed video frame. This errored frame can be any video frame from low resolution videos to live 4K videos. We have three samples of data here in figure 3, which are errored first and then error concealed using two existing methods and our proposed method. Our experimental results show that our technique has a better quantitative performance in video error concealment, on average 7% and 5% PSNR increment, 43% and 31% decrement in MSE with respect to motion vector estimation and error concealment using neighboring motion vectors method, respectively, and slight increment in MSSSIM and UQI values. Our future work would be to train the proposed model with more data sets so that the accuracy increases. We can also optimize the model to increase performance. Thank you.